So the next speaker is Nitica Sakharwade from Perimeter Institute, who is finishing, I think, her PhD with Lucian Hardy, and she'll tell us about the Causaloid framework.
Thank you, Lydia. I hope everyone can hear me. Yeah, I'm not sure if my video is also still off. I think it's off.
It's off at the moment.
Yeah, okay. So I'm going to talk about revisiting the Causaloid framework because we want to talk about a hierarchy we found with respect to the third level of compression that I will explain through this talk. And it's very exciting to look back at a paper and find something new there. So I'm happy to talk about this. This work is with Lucian Hardy, and he's around in this conference, but I think he's not here right now because of the times in Waterloo being before waking up time. So yeah. So let's see if this works here. So I want to first talk about the Causaloid framework very quickly because I don't want to assume that everyone would have heard about it. And the way I would like to do that is by asking you to think about a person in a box, in this case, Lucian without loss of generality. And this person has a lot of cards, stacks of cards, which have information data collected from procedures done outside of this box. Now, this person cannot look outside this box for clues, and all this operational data is available, and this person's trying to find out something about the physical theory that generated this data. Okay, so that's the premise. And what kind of data is there on the cards? So we have X that maps location. Now, it would be generally like the notion of location is not tied to any physical theory because we are trying to have a general notion here. But you can think of it as like space-time events analogous to that, if you'd like. You could even have, like if you had a GPS tracker or something like that, then you could note down the location from that, depending on what experiment you have and what measuring devices you have. Okay, then you have actions done at this location and some observations found. So now you can form sets from these stacks of cards. And one kind of set you can form is all cards that have X written on these cards. Okay, given some region, given some X location, you can find a stack of cards for procedures, which would be an intersection between all procedures and any card that matches this location. So, and similarly, you can have a set for outcomes. So it's natural to expect that the set for the cards within a region is bigger than the procedures, which is bigger than the outcome. Okay, and now a core belief is that any physical theory must correlate this recorded data. So the idea here is that all logically possible cards are available in this stack of cards, but we want to do physical compression on these cards. We don't want to be working with all these cards. We want to find a systematic way to find the minimum number of cards we actually need to predict anything in the physical theory if someone asks us to predict. Okay. So before we get into the 3 levels of compression that comprise the Causaloid framework, the precompression phase is already where we are interested in the probabilities given some, for some outcomes, given some procedures. So we are focusing on some region Ri. And now for this Ri, you think of everything outside that Ri, let's say where there's a bigger set of regions R. You want to think of that as being a generalized preparation for Ri. And now you want to think about the measurements for Ri as the procedures and outcomes you have, and they are labeled with alpha, which is just a label to figure out all the procedures and outcomes you can have. And this, we'll just say that this label alpha belongs to a set gamma, which is very big because you can have an infinite number of measurements in there. Okay. And we are interested, so this is the probability we are interested in, P alpha. And to begin with, after we have organized the cards with respect to regions, and so one can write this down simply as some generalization of a bond rule, if you will, as an inner product between R dot P. And here, like, we haven't done anything fancy. It's just, P is just a list of probabilities, P alpha. So it just literally lists all the possible probabilities with respect to this region Ri. And then R is just, you can think of this as picking out. So it is all zeros except for one in the location of the alpha ith position. And you can get the probability. So that's one way to predict, but we still have a very long list of vectors here. Okay, so now we'll go into the crux of the framework. So the way I want to go through this framework is by bringing us back to this image, and we'll use this diagram to explain all the levels of compression. Okay, so we want to explain the Causaloid framework first, and then after we've done that, we will introduce a hierarchy for physical theories with respect to this framework. Okay. So now you can consider any number of regions, but for the sake of exposition, I am considering 3 regions. And now we want to focus on this particular part of this diagram, which pertains to the first level of compression called tomographic compression. So now what we have here is we are still interested in the same probabilities, but instead of the capital R and the capital P, we have replaced it with these new vectors, these smaller vectors. And how do we do that? Essentially, you would say that any region would have a fiducial set of measurements that are sufficient to characterize any other measurement outcomes in that region. So this is related to the concept of tomography of a region. And what one would do is pick out this fiducial set omega. So for finite dimensional systems, you would have this to be a finite set. And so now this P is just a list of probabilities for the labels L, which are contained here, but omega is a subset of gamma here. Okay. And then R is not anymore just zeros and ones. For the label where alpha equals to L, you would have it to be, again, 1 in the position of alpha, but 1 in the position of alpha equals to L. But for a general alpha, you would have some other vectors. And given the data, you can organize this such that you write down a compression matrix lambda here, where these are your, so to say, basis R's, given your fiducial set, which may not be unique. And then you can find it as, this is the compressed version, and you can decompress it with your compression matrix lambda to get R alpha, which you can put in here to predict any probability again. Okay, so this is pertaining to a single region, and we would call this tomographic compression or first level compression. So now coming back to this 3-region picture, you would say that you have understood this 3 parts where you have 3 regions, and you did first level compression on each of them. Okay, now what's next? Is this sufficient? What happens when you try to compress further between 2 regions? Okay, so now we will focus on this bigger lambda matrix. And this comes through the notion of compositional compression. So now this expression is slightly different. We have Ri's and Rj's, and then everything else in R. And now we want to do predictions for joint predictions for outcomes within these two regions. So how would one do that? One would go about doing the first level compressions on each region, but this might not be sufficient. So imagine you have two regions that are a tensor product with each other. So like think of a quantum state, two states, and now you cannot do further compression on them because they do not reduce the degree of freedom between them. But if you imagine a gate A followed by a gate B, then they're causally adjacent and they give you a new gate C. And this C would have fewer parameters to describe it than A and B would. So this is what would comprise in this compression, the second level compression. So you can consider two or more regions. Again, for exposition, I'm showing two regions. So now, if once you had first level compression, you would have the labels alpha Ri and alpha Rj living in the Cartesian product of the omega sets with respect to their first level compressions, the tomographic compressions. But then more generally, omega R1, R2 here, but consider this I and Rj in general, would be smaller than this Cartesian product. And so now we do this label change from L's, which was the tomographic compression, to K's. And this is given by this compression matrix. So just checking the time. Okay. So now we have, what we have here is we've done first level compression on this image, and then we have second level compression between region 1, 2, 2, 3, and 1, 3. And that is all the kinds of compositional compression you can do per two regions. But now you can also do compositional compression for all three regions. And that is denoted by this box here. Okay. So now we are finally ready to tackle the last level, or the third level of compression. And here it's called meta compression because it's actually compression over the lambda matrices that we just defined. For the case of just three regions, all you have is lambda matrices pertaining to one region, compositional compression pertaining to two regions, and compositional compression pertaining to three regions. Of course, the list will go on in a general setting where you have more regions, but let's just consider this for now. And essentially, if there is any redundancies here, you would have some rules that would finally give you what is called the Causaloid, which can be used as a product. So remember that we were interested in R alpha, Ri, Rj, and so on. And if you have a bigger R of that form, then once you have done all these compressions, you find the Causaloid and you say you have everything that you need. And you use that to find the products between these R's. Okay, so that is meta compression. And meta compression is interesting because we were able to study this further and find a hierarchy with respect to this. Okay, so what are we doing now? So the question we are asking is, okay, look at this image that we have been looking for the last 5-10 minutes. And here I've removed all compositional compression matrices for two regions. And now we say these will always be equal because I've already applied the third level compression box here. So this is an equality, and this is just to show how it would look like, but the details are not important at this stage. What you need to know is these are the first level compression matrices, and these are the second level two region compression matrices, and this is the second level three region compression matrix. So I've just written the analogous equation down here. And the question we are asking is, when is, for example, So we talked about rules in meta-compression of how we would find redundancies in the set to find the causaloid. And now the question is, okay, if you have only two region compositional compression, is it sufficient? And to do that, if you can find, you can solve this equation to find that this is essentially not doing any compression in this equation, then what you can do is you can find a form for any three region compositional compression with respect to two region compositional compression in this equation, if you see here. So focusing on this equation quickly, if you have three regions with the causal structure that we had it assumed till now, where R1 goes to R2 goes to R3, then you can write down the lambda matrix for three region compositional compression in the form of two region compositional compression. And then the omega set also takes a particular form. So generally, this is what would give you a hierarchy. So now, like, this is an equation that gives you the general form for any omega for any n region with respect to given. So you would find the smallest d. So the smallest number of regions for which you need to consider compositional compression, such that any other compositional compression can be expressed in that form. So then that is to say that you don't need to do n level compositional compression where d is sufficient. So what are we doing here? This is just an omega set for d regions. And then we do filling. So if you look here, we have, this is what we do. So the filling is essentially if you have three regions and you have, so here n equals to 3 and d equals to 2. So if you have omega for two regions, then you fill it with every other region such that you can compare this. And so that is what filling does to n regions. And then O is just ordering amongst these indices. And then you take the intersection over all these forms, all these terms. And then what you get is a hierarchy that we are still trying to study. It's an open project. It's a huge project at this point. So for d equals to 1, you have no causal structure. It means that compositional compression is not required. So you do your first level compression on each region and you're done. I would have to think what would be a physical theory that would fit that, but you can think of just a lot of quantum states that have no causal channels between them, and that would fit this d equals to 1. But that's not a physical theory, that's just an example. Okay. For d equals to 2, we have quantum theory and classical probability theory fit in that. And we show this through the duotensors. I'll show this in the next slide, depending on how much time I have. And then we are trying to populate this hierarchy and construct the d equals to 3 and 4 cases. Essentially, what we have there is instead of wires which we have in circuits, we are trying to generalize those to hyperwires, so to say. So that connects 3 regions at a time. And then the notion of causality becomes quite vague in those settings. An open question is also to figure out where the current models of indefinite causal structure would fall into this hierarchy. And that is an open question at this point. Okay, so lastly, to give you some handle on this hierarchy and the equation I was talking about. So here, we talked about this causal structure and this general form for the omega. But now let us consider the duotensor case. So imagine just a quantum circuit. This is a gate A, B, and C that are connected so with this causal relation. And in the duotensor framework, we would expand it as this. I am actually leaving out the details for the duotensor framework at the moment, but I just want to give you an idea at this point. So then you can bend around all these wires without any repercussions. And you can try to bend it to see how it would look within the Causaloid diagrammatics. So here what's happening is, okay, so we talked about the omega sets that you get from tomographic compression. In the case of the dual tensor framework, which includes quantum theory, what you would have is the omega set for A actually factorizes into the past line and the future line. So yeah, because of the structure of the wires and the structure of causal structure in quantum theory, you can actually write it down as so. And then what you show is that when omega, for example, here, omega A plus and omega B minus are actually redundant degrees of freedom because they form a channel. And so you end up getting just, for example, if you look at omega AB here, you actually get the compressed version between them would be omega A minus, and then single elements, and then omega B plus. And similarly for omega BC, we have a similar notion of compression, but for omega AC, since they are not causally adjacent, no such compression happens. Okay, and then you can also find the omega set for ABC, and this is just to show that this falls into this form, the general form that we found. One can check that. So this is something we are working on, and then yeah, finally we are working on the population of the hierarchy. If anyone is interested or wants to talk about problems in this area, I'm happy to talk about them. There's a lot of questions that need to be answered at this stage. So yeah, thank you. And yeah, I'm happy to take questions.
Thank you, Nitica, for this very interesting talk.